Car on the sphere. In this exercise, we consider a car moving in the plane, and later it will move on the sphere. When it moves on the plane, it is described by this state equation. So x1, x2, x3 corresponds to the pose, x4 is the speed, and u1, u2 are the controls. So the control, they are known, they are given by this expression. For the first question, I have to give the shape of the manifold corresponding to the state space, and then I will have to simulate the system. So first I have to notice that the state at time t equals 0 is given by 0. It means that there is 0 speed, the position is 0, 0, and the heading is also 0. So here it is my car given here, where I have x1, x2 corresponding to the coordinate x1, x2. The heading is x3, and here x4 is the speed. So I have this state equation, and I know that u1 here, I know the expression, it is given by O dot 1 cosine of O1t plus O.02. And for U2, it is given by 1 minus x4. So what it means? It means that U1, it corresponds to the direction. It's oscillating with a frequency given by this. And due to this, it means that the oscillation, there is a bias, and the car will turn left. Oscillating, but turning left. And here, it means that U2 corresponds to the acceleration. And due to this, it means that I have some kind of proportional control for the speed. And if I have an error between the speed I want 1 and the speed I have, x4, then I will accelerate. So it's some kind of proportional control. So for the first question, I have the state x, which is equal to x1, x2, x3, x4, and x1, x2. x1, x2 corresponds to the pose, and they both belongs to R. Both belong to R. x3, it's an angle, so I will see that later, and this one is the speed, so we can say that x4 also belongs to R. But this one, it is an angle, so the angle does not belong to R like it is given here, because x3 and x3 plus k2 pi are equivalent. So it means that the set of angles is not like this, it's not R, with a 0 angle here and 2 pi here. No, it's not like this, because I have some angles that are equivalent. It is the set of angle, it is a disk like this, with an angle equal to 0, and the manifold corresponding to this is R with a quotient by 2 pi z. So it corresponds to the unit circle. So here it is R quotient with 2 pi z due to the equivalence relation. So this set is a trigonometric circle and also correspond to what we call SO2, the set of rotation of the plane. For the simulation, I propose the following Python program, which uses roblib library. I take 2000 for the number of iteration, a small dt of 0.1, the sampling time, and for the initial state, I put 0, 0 everywhere, so I have the program is in scalar form. So that's why I put x1, x2, x3, x4 corresponding to this. So for all k, I will here compute t. Every 40 iteration, I will draw the car using this statement here in dark blue. I will wait 0.01 second, and here it is a Euler formula given in a scalar form. So I can recognize here I have this, so this corresponds to dx1, here to dx2, u1, u2, and u1 is given by this, and u2 is given by this. And here I will use an Euler formula for integrating my state equation given here. So here we can see that x3 is a floating point number, and I will not compute in the circle. It means that maybe one day x3 will be larger than 1000, for instance. It is not always on the disk. And in this application, it is not important because I have no singularity. This is for a complex reason of topology, but when I deal with three angles, like phi theta psi is a Euler angle, then we may have some singularities in the representation due to the fact that the shape of the manifold, so this is a manifold, some kind of surface, has poles. So this one has no poles. I can bisect like this without problem. When I have something like a sphere like this, I will have some poles, and it will be difficult to represent by parameters, such that angles, without singularities. But here it's not important in the plane. So I switch to Python here. I run the program, and I can see that the trajectory from the initial condition, and we can see that I turn left, oscillating as we wanted. Question number 2. I take the same car with the same input, but now the car moves on the surface of a sphere. The diameter is 20 meters, and now I have to give the shape of the state space as previously. So this was my state equation in the plane. Yes. And remember that in the plane, I had the state space for x1, x2, x3 was x4. So the state belonged to R times R, so for R1, R2, times R quotient to PZ times R. Okay, so this was some kind of cylinder, high-dimensional cylinder. Now things are different, because I cannot represent the position by x1, x2, but by a point in the sphere, like this. So this is a position which could be represented by x1, x2. And I cannot represent the state space in by Cartesian product of sets like this. Things are more complicated. So if I take the block like this, of x1, x2, x3, so which correspond to a pose like this one for the car, then we can, this set, so x1, x2, x3, corresponds to the pose, belongs to the set of rotation SO3. So it means that a pose corresponds to an orientation. And to understand this, I propose the following figure here, like this. If I take a pose like this one, just in the center, and any kind of pose, this one, then we can see that I can go upward, up to the surface, and to have a pose of my car on the surface. So an orientation, we can associate one pose. And if I have one pose, like the red car, I can associate an orientation. So the orientation can be represented by a matrix, a rotation matrix. So I will try to call it R of t when it moves with t. And I can also represent the pose by R of t. So x1, x2, x3, we can understand that it corresponds to an orientation, and it is an element of SO3. So the state space for x belongs to SO3, the set of rotation, but I have to add this one, so Cartesian product with R. This is a manifold of dimension 4, and this was also a manifold of dimension 4. But this one, I am able to parameterize this manifold, but not this one. I can try to represent, for instance, this one by Euler angle to find a parameter, phi, theta, psi, and this one I have no problem, it will correspond to x4. But this parameterization contains some singularities, and I have to try to avoid it if I want to move freely on the sphere without meeting any numerical problems. Question number 3, I have to provide a simulation of the car moving in the sphere. And of course, this simulation should not use Euler angles. I have to avoid all possible singularities. So I propose to use this library available here for drawing in 3 dimensions. Again, I will take this dt and a number of iterations, but first I will draw the sphere here in cyan with a radius equal to 20 meters. I will give an orientation, because the orientation for the car, I recall that I will represent by R. So SO3 is a manifold of dimension 3, but I will embed it in the set of matrices, which is of dimension 9. So if I want like this, it is a set of matrices of dimension 9, 3 times 3. And here I have some strange object of dimension 3, which corresponds to SO3. I will be able to compute with floating point number inside this embedding, but not here. So this is why here I will use matrices to represent my rotation. Here it is identity. I will draw the car, a large car, I multiply by 5 here. I run it, and it generates the file car.obj. I go to 3dviewer.net. I upload the file, and I can see the car with the sphere. My state x can be represented by a rotation matrix R and the speed x4. So x4 can be represented like this. The set of poses, so R, the rotation matrix R of t, we can say that it belongs to SO3. Normally it's not exactly this, but I write like this. So it is a Lie group. It is a Lie group. And when I want to move inside a Lie group, I go to the origin, so to R equal identity, which corresponds to a pose given here. So I represent my car here at 0. Here. And then I will move on the Lie algebra. And the Lie algebra corresponds in this situation to vector of rotation. So this one belongs to R3. Okay, it's a Cartesian space. And in my situation, omega of t correspond to how I move when I move in the sphere with a speed equal to x4. So first, we can see that I have x1 corresponding to this direction, x2 to this direction, and x3 on the other direction. due to the fact that I have x4, I can understand that I will rotate in this direction, and this is why and I will be proportional to the speed. This is why here I will have something like x4 divided by r, where r is the radius of the sphere. When I want to turn around x3, it will be due to the change of heading, and this is tuned by u1, like this. And now, if I want to tune with respect to x1, in my situation it is not possible when I move in the sphere. This is why here I will have 0. Okay. As a consequence, I will have the evolution r at time t plus dt, which will be given by my r of t multiplied by the exponential of this one for a time equal to dt. So dt multiplied by omega r vector product. So this corresponds to the adjoint of omega r, and it is a skew symmetric matrix. This one is almost 0 due to the fact that I have dt. So this one is almost equal to identity. This means that r of t plus dt is almost equal to r of t. So it is the evolution of r of t. And now for the other one, for x4, I will have x4 at time t plus dt, which will be equal to, so here I represent with an Euler formula, x4 at time t plus dt multiplied by the acceleration u2 of t. So this is the formula I will have to program for my simulation. For the simulation, I take 2000 iteration, the sampling time, the radius of the sphere. I will generate the file car.obj. I draw the sphere, and this is my initial vector, my initial state. So of course, I have my state x is made with the rotation matrix at time 0 and the speed at time 0. This one is taken as the identity, and this one as 0. I have my loop. I compute my time t. I compute my input u1, u2, as it was the case for the plane. Now, for the integration, I will use this formula. So it can be interpreted as an Euler formula for integration, except here, where I use multiplication and not addition. This formula here, the adjoint of this, so this one corresponds to omega r, the rotation vector expressed in the car frame. Then I compute, I multiply by dt. I take the exponential here, so it's the exponential matrix. I multiply by r to compute the new r at time t plus dt. And this one, it is the Euler formula given here. And every 20 iteration, I will draw the car in red and not too large to avoid overlapping. I run my program. I visualize it, and I obtain this. The initial condition is here, just at the North Pole. The car, it accelerates, we can see, due to the overlapping we have at the beginning, and after it reaches a constant speed equal to 1, as expected. My trajectory is represented here, and on the left I have a zoom, with the initial position R0, which contains the position but also the heading. We can see that I have an acceleration due to the overlapping here. The orientation at the beginning is R0 equal to identity, and I see that I am aligned with the axis. Okay. The trajectory on the sphere corresponds to one trajectory in SO3. Recall that I have to add R to have a representation of the state space. In the trajectory here, I have one loop, so importance for slab technique to detect loops. Here I see that I have one loop where I go to the same place at two different instants. We can see that for the same input on the plane, I have something which is different, because here I have no loop, where here, due to the sphere, I am able to see that I have one loop.